Hi, I'm Dean, and I'm presenting on sparsity awareness in distributed computations. Let's start with a quick 1-minute overview about what it is that we do. First, we start with a key observation which holds in many distributed settings with respect to the density and sparsity of an input graph. To leverage this observation, we introduce a model tailored specifically towards it. However, this model is not something natural. It's not something that's supposed to appear in practice. And so we show how to simulate this model in existing distributed settings. All in all, this gives us two things. First, we show a central framework for data-heavy problems. That means solve data-heavy problems using our observation in the model we introduce, and then have the solution translated automatically to many different distributed settings. Using this, we managed to show fast distributed algorithms in two different models for computing distances in graphs. Let's start with the two models where we have our end results. First is the Congest, a well-known distributed setting whereby we have a graph composed of nodes and edges, where the nodes represent computing devices and the edges are communication links between them. In every single round, two nodes with an edge between them can send a log n bit message to one another. And we desire to solve problems in this way. In the Congest setting, our main complexity measures the number of rounds that it takes for an algorithm to converge. Recently, the hybrid setting was introduced. The hybrid setting is very similar to Congest with two main differences. First, two neighboring nodes can send messages of unlimited size to one another in every single round. And the second, we have an overlay graph. This means that every single round, every node can choose log n nodes in the graph, arbitrary nodes, and send a log n bit message to every single one of them. This was introduced in order to see how local communication and global communication interact with one another, and many interesting results were shown in this model. Again, the complexity measures the number of rounds that it takes to converge on a solution. The results we show in Congest are density oriented. This means that the more dense the input graph, the faster the result. We begin with showing an approximation for weighted all-pair shortest path. That means that we want an approximation for every single node to know the distances to every other node in the graph. Our solution runs in roughly linear rounds times the mixing time divided by the minimum degree of the graph. The mixing time is roughly the number of iterations it takes for a random walk to converge to the stationary distribution. The key point is that in many graphs, the mixing time can be, for example, polylogarithmic. In such cases, the minimum degree doesn't even have to be polynomial for us to get a round complexity which is less than n rounds. That is little o of n rounds. And this is interesting because the other results currently known in Congest all take at least a linear number of rounds for solving APSP or approximating it. Second, we show exact single source shortest paths. This means we have a single node in the graph, and every single node wants to learn its distance to this node. Now, our solution runs faster the more edges exist in the graph. Specifically, if we have n squared edges in the graph, that means the graph is very, very dense. Our solution takes n to the 1 over 6 times the mixing time number of rounds. This should be compared with all existing solutions for approximating or exact single source shortest path, which take at least square root of n number of rounds. Recently, a 1 plus epsilon approximation was shown for single source shortest paths in roughly mixing time rounds. This is faster than our result, however, it's an approximate result and not exact. Finally, in the Congest, we show how to simulate the congested click model. This model is much stronger. In the congested click, every two nodes can send a single message between them every single round. We should compare this result to the previous state of the art, which was slower by at least roughly the average degree in the graph. And we should see that our simulation is tight in some sense. That is, a trivial lower bound is n squared divided by m rounds, since in every round of the congested click, n squared messages are sent. And the Congest has m bandwidth per round, and therefore this is a trivial lower bound. And our result is roughly that times the mixing time. In the hybrid setting, we show one key result, approximating single source shortest paths, and this in return shows a result for an approximation of diameter. The interesting part about our result is that it's the first result below n to the 1 over 3 rounds for these types of problems. Many other algorithms are known which run in n to the 1 over 3 rounds for these types of problems, as well as lower bounds for similar ones. It's also noteworthy that in the hybrid setting, APSP and all its approximations take exactly n to the 1 over 2 rounds. So how do we do this? We do this in 3 steps. Let's start with the first one, our key observation. It's a key observation, but it's a rather simple one. In sequential computing, when an input graph is sparse, it might take less time to solve the problem. That also holds in the distributed setting. However, what doesn't typically happen in the sequential setting, but sometimes does happen in distributed, is that the more dense the graph, the more bandwidth we have. That means that sometimes in the distributed setting, if a graph has more edges, we have in total more bandwidth, more messages can be sent per round. And perhaps this can help us solve problems much quicker. And so we would want to use this observation. We would want to use this in order to show algorithms such that if an input graph is sparse, it leverages that. However, if it's dense, it leverages the fact that you have more bandwidth. We see this in the hybrid setting, whereby our result depends, on the one hand, on matrix multiplication, which works well in sparse settings, because it's based on sparse matrix multiplication. And on the other hand, we show that when the graph is dense, we can quickly simulate the broadcast congested click, where the broadcast congested click is exactly like the congested click. However, every single node needs to send the same message to all the nodes in the graph in every round. Both of these algorithms are great in their own domain. The matrix multiplication is very fast on sparse graphs, and the broadcast congested click simulation is very fast on dense graphs. However, when we flip the domains, they run much, much slower. The matrix multiplication runs very slow on dense settings and vice versa. However, when we combine them and use each in its own domain, we get a result which is better than the state of the art for single source shortest paths and weighted diameter approximations. Okay, having this observation, we don't want to repeat the same process every single time for every single problem in every single model. And so we introduced the anonymous capacitated model, which is supposed to aggregate all of these computations. The goal of the anonymous capacitated model is to provide a unified environment for solving data-heavy tasks in distributed settings, for example, matrix multiplication and distance computations. We would want to solve these problems only once in this setting, and then have them automatically translated to many distributed settings at once. To do this, the first thing that we have to do when defining the anonymous capacitated model is to, 1, ensure abstract routing. That means we don't want to be dependent on the routing of the underlying model where we simulate the anonymous capacitated. And we want automatic load balancing tools implemented within the model itself. Therefore, we define the model as follows. First, it's a synchronous model. We proceed in rounds, and in every single round, every node can send C messages for some value C. It doesn't have to be a constant, it's just some value parameter of the model. Now, how do we send these messages? Every node has a O of log n bit communication token, and every node can either send its messages using one of 2 ways. Either it randomly sends a message somewhere to some random node uniformly at random from the graph, or it sends a message to some node which it nodes the communication token of. This definition allows us to abstract the routing of the underlying model over which the anonymous capacitated model is simulated. All the nodes are basically symmetric in terms of the number of messages they can send per round. And if we simulate the anonymous capacitated model, for example, in the Congest, the designer of the algorithm, the designer of the simulation, can take the exact way in which messages are sent in the Congest and shove that routing information into the communication tokens. And basically, since a node can either send a message randomly in the graph, or it can send a message to a node whose communication token it knows, the communication tokens allow us to abstract the way in which routing happens in the underlying model. Now, in the anonymous capacitated model, we present many fundamental tools based on an existing paper from the congested click. These tools include sparse matrix multiplication, an efficient construction of hop sets which allow distance approximations, and, well, distance approximations. But if we just take an existing paper from the congested click and implement it in the anonymous capacitated model, so what's the new challenge here? What's the big thing that we have to tackle? Well, that big thing is load balancing. In the congested click setting, the previous paper, as well as many other papers, typically assume that it's okay to perform some load balancing before we start the algorithm. However, in this load balancing, it's typically assumed that every node can send theta of n messages just for the load balancing. Now, in the congested click, this can take O of 1 rounds, and that's perfect, and therefore it's totally okay in that setting. In the anonymous capacitated model, however, this is totally infeasible, because sometimes the value C, that is the number of messages every node can send and receive per round, can be significantly lower than n. And thus, these load balancing would become a problem. Therefore, we introduce the Keren configuration. Imagine a typical distributed setting, such as the ones which we introduced. The input graph is usually held in a way whereby every node knows its neighbors. However, this can provide some very skewed input distributions. And so the first thing that we'd want to do, we'd want to translate this into a situation where every node holds roughly the same number of input bits. However, we don't just have some general distribution of input bits such that every node has roughly the same number of bits. We do this in such a way where it's possible to perform simple fundamental transformations on the data in such a way that every node still has roughly the same number of bits. And these transformations are complex enough to be able to quickly implement operations such as matrix multiplication and distance computations. Basically, we move the graph, we move the representation from some skewed distribution to some normalized distribution. And then we perform transformations while keeping it, making sure that at every state, no node holds too much information. And then we reach some final state. Now from this state, two things can happen. Either we can create some final output. For example, if we want the diameter of the graph, we can perform some aggregation function across all the nodes and get some final output. Or we can convert the information back to classical storage, whereby every node knows some information regarding the neighbors that it has. In either case, most of the heavy computation was performed using these transformations in the Keren configuration data structure. And so basically what that gives us is fundamental properties of the Keren configuration. It's really efficient to construct from a given input graph. And we have this large framework which allows us to perform many operations inside this configuration. Now this framework works by depending on the average load used within the operations and not the maximum. This makes it very convenient for an algorithm designer to just focus on the total complexity of an algorithm, the total message complexity of an algorithm, and not the skewed distributions which might happen due to skewed input. The nice thing about the Keren configuration is that it works in the anonymous capacitated model, and therefore it directly works in every single model which simulates the anonymous capacitated. Directly it works in the congested click model, as that is just an expansion of the anonymous capacitated model, and it works in any other model which simulates the anonymous capacitated. Finally, it makes it that it's easy to implement very complex operations without having to consider load balancing. Therefore, we can implement these operations once in the anonymous capacitated and then get them everywhere in many different distributed models. And so let's show this final part. Let's show how we take solutions from the anonymous capacitated model and simulate them in existing distributed settings. We begin with showing how to simulate the congested click and the anonymous capacitated model. This is rather typical. Every single node in the graph has n messages which to send per round. Therefore, it randomly selects C messages every single round and sends them for n divided by roughly C number of rounds. For example, if C equals 2, every node selects roughly 2 messages, say the purple messages, and sends them, and then selects 2 more messages randomly, say the green messages, and sends them as well. To simulate the anonymous capacitated model in the Congest, we need some fundamental observation. The main problem here is low degree nodes might not be able to send too many messages. In the anonymous capacitated model, every node can send the same number of messages. High degree nodes in the Congest will be fine with this, but low degree nodes will have some trouble. Therefore, we split the nodes into 2 parts, low and high degree nodes, dependent on if they have more or less degree than the average degree divided by 4. We see that if we define the low and high degree nodes like this, then the edges incident to the high degree nodes are at least 7/4 times the number of edges in the graph. This implies that most of the bandwidth of the graph is contained within the high degree nodes, and therefore it's possible to just use them and ignore the low degree nodes. So how do we do this? We have every high degree node simulate many low degree nodes by learning all of their input information, and then we just have the high degree nodes communicate between themselves and finally send back the output to the low degree nodes. How do we simulate the broadcast congested click in the hybrid setting? Imagine we have this input graph in the hybrid model. And we have a node which wants to send a broadcast message to all the nodes in the graph. Let's have the node send the message randomly a number of times to random nodes in the graph. Now, we'll have all the nodes learn all the messages which landed in their vicinity. In dense regions, with high probability, every single node would have received the message. However, we can have some sparse regions which didn't receive the message at all, and so these nodes won't hear the message being broadcast. Therefore, we just focus on the dense regions. These regions are such that they can hear all the messages being broadcast, and we use them to simulate also the sparse regions, basically in the same way which we did previously when simulating the anonymous capacitated model in the Congest. Finally, simulating the anonymous capacitated model in the hybrid setting is roughly a combination of the previous two simulations. So let's recap about what we did. First, we have a key observation which holds in the distributed setting and is very different than what typically happens in the sequential setting. In order to use this observation, we introduce an auxiliary model which is not meant to be something practical or something in nature. And we show in this model a very complicated toolkit on how to exploit this observation and how to perform data-heavy problems all in this model. And finally, we show how to get our results from this setting and use them directly in many different existing models in the distributed setting and get end results both there and an entire framework which could be useful for potential future work. That's it for today. Thanks.